But let's just focus on what we are predicting today. So, in our investigation, we want to identify the predictors for coronary heart disease status on the participants of this synthetic, say, synthetic study, because it's a synthetic data set. So, if you have a background in healthcare, you are familiar with coronary heart disease, but I will provide a brief overview for the broader audience in the channel that is less familiar with the term. So, CHD, or coronary heart disease, is a term describing a state in which the coronary arteries are unable to supply oxygen, rich blood to the heart muscles, which is the myocardium, because there is some buildup of fatty substances or there is some sort of coronary artery vasospasm. So the arteries are kind of constricted. It's like if you have a pipe that is obstructed and it cannot allow the fluid, and in this case, the blood, to flow freely. So you can see here there is like this snapshot of this artery, and then you can see this yellow part within the arteries that is making the space for the blood flow very, very, very narrow. And you can imagine why this is problematic. So again, the coronary arteries are those ones here. So here you have the left coronary artery, then you have here the branch of the right coronary artery. So a simple way to think about is that regularization tries to prevent large, noisy residual patterns by making the model less flexible. So we'll start by modeling a ridge regression in this workshop. So we'll pull coefficients closer to zero by using ridge regression, and then it will make the model less sensitive to noise and multicollinearity. If you were to compare ridge regression or regularization methods in general with the frequentity statistics. For instance, ordinary least squares estimates coefficients by minimizing the sum of square residuals with no penalty. However, ridge regression also minimizes square residuals, but it adds a penalty term. So it trades a little bias for lower variance. So in summary, ridge chooses the penalty value to balance the trade-off between feed to the training data, so lower training error, lower bias, and simplicity of the model, so smaller coefficients, lower variance. And I have this figure basically to show you how it works. So if you have a small penalty value, so it means you have a weak regularization, your training residuals are smaller, as you can see here. They're the false negatives. So these are actually coronary heart disease cases, 1.1%, but were predicted as non-coronary heart disease cases. And then in the bottom right, you have the false positives. So these are actually non-coronary heart disease cases, but were predicted as coronary heart disease cases. And then in the top right of your screen, you have the true positives. Only 3% of true coronary heart disease cases were predicted by the model as coronary heart disease cases. And so the model has like a sensitivity around 8%, specificity around 98%, and accuracy of 67%. It means that the model is much better at identifying non-coronary heart disease cases than correctly detecting coronary heart disease cases.